Is my dad cheating? My family loves playing Settlers of Catan, but my dad always seems to win, despite his questionable strategy. In the game, you place settlements on a hexagonal board with tiles that have numbers. When a number is rolled, you get the resources from that tile if your settlement is on it. Then, you use those resources to build things like settlements and cities, earning victory points. The first to 10 points wins. Each number has dots representing its likelihood of being rolled. With the more dots a number has, the more likely it is to occur. Based on this, the strategy becomes to place settlements on spots with more dots in order to get more resources. And yet, I swear every time we play, my dad places his settlements on the less likely numbers and still wins. So, is he cheating by rating the dice, or am I just bad at the game? To find out, I've designed an experiment that will prove whether or not the dice are rigged when my dad rolls them. But first, we need to collect data. This means convincing my dad to roll a couple of dice 120 times. Surprisingly, he agreed, but not without reminding me it was a waste of time. Honestly, it wasn't even that hard, and it didn't even take that long. In fact, I probably had the harder job because recording that data by color was trippy because the red dice had yellow dots and the yellow dice said, you know what? Never mind. Anyways, here are the results. Now, what am I going to do with these numbers? Well, if we were to consider that the dice are fair, then every number has a 1/6 chance of being rolled. And so if each dice is rolled 120 times, we expect each number to occur 20 times for each dice. This is the expected distribution. However, I think that when my dad rolls a dice, it's unfair. So by comparing the observed distribution from him rolling each dice 120 times to what's expected, we can determine whether or not he is cheating. For now, let's just consider the yellow dice. One way to compare the observed distribution to the expected distribution is to find the difference between what's observed and what's expected. Then, we can add those differences. However, the problem with this is the differences can be either positive or negative, so adding them up cancels them out. To prevent this, we can square all the values. Another option is taking the absolute value, but squaring the values gives more significance to larger differences, so let's stick with that. The final issue that needs addressing is that the values aren't standardized. For example, when compared to 5, 10 is much larger than 105 is when compared to 100. However, calculating the difference and then squaring it doesn't reflect this. So to put the size of the difference into perspective, we can divide the squared difference by the expected value. This allows for fair comparison regardless of what the expected values are. Now, we can add all the standardized differences together, which gives us what's called the chi-squared statistic. This value is equal to 5.2 for the yellow dice, and following the same process gives 8.3 for the red dice. But why calculate these numbers? Essentially, we are doing a chi-squared test for goodness of fit, which is a test to determine how likely an observed distribution is based on the expected distribution. The chi-squared statistic is a value that measures how far off the observed distribution is from what's expected, and it can be used to determine whether or not my dad is cheating. To do so, let's use the chi-squared probability distribution. This distribution's shape varies based on a metric called degrees of freedom, which is a fancy way of saying the number of categories minus 1. Minus 1? But why? Well, since the standard dice has 6 numbers, there are 6 categories. If we know the total number of dice rolls, which is 120, and the counts for numbers 1 through 5, the number of 6s is determined. Minus 1 gets rid of the category whose value is fixed and can't be anything it wants to be. So, we use a chi-squared distribution with 5 degrees of freedom. A property of probability distributions is that the area underneath the curve always equals 1, representing the total probability of all possible outcomes. This is important because the area can be used to find the probability of certain outcomes. Here's how it works. Since the chi-squared statistic measures how different the observed data is from the expected data, bigger values are less likely if the distribution is what's expected. This can be seen in the chi-square distribution, as generally, bigger values mean less area is under the curve. To determine the likelihood of our observed data, we can graph the chi-squared values for the red and yellow dice and find the area under the curve to the right of these values. This will equal the probability of getting our observed data, or data that's less likely. If this probability is low enough, we can conclude that our data is statistically significant and likely not due to chance. In other words, it's most likely the actual distribution isn't equal to the expected distribution. Typically, the level of significance, aka alpha, used is 0.05, meaning that if the probability found is less than 0.05, we have enough evidence to conclude that my dad is cheating. To find the area's value, we can use a graphing calculator like a TI-84 and a function called chi-squared CDF, or cumulative distribution function. Alright, so here's the moment of truth. For the yellow dice, the probability is... what? 0.392? I thought that'd be like way less, but like that's not even close. You know what? It's fine. We still have the red dice. And the chi-square statistic is larger, so... alright, please. Come on. Please. Here we go. Come on. Please. Please. Oh, no. It's 0.140. Why? I mean, like, he literally rolled it 31 times. Come on. Well, I guess that answers the question. It looks like my dad isn't cheating. And I'm just bad at Catan.